solving a system of linear equations by graphing. So the first system we're going to look at is y equals 2x plus 1 and y equals 4 minus x. And so now remember that the basic idea here is that we're looking for the solution to be the point or points that make both of those equations true at the same time. We want to find their overlap. So what I want you to think about is, as far as graphing is concerned, now taking a step back, the big idea of graphing is to get an overall understanding of what a solution to a system's of equations is, to consider the big picture. That's really what we want to do here. So when we think about the line y equals 2x plus 1, and we graph that using a slope of 2, y-intercept of 1, what we're actually doing is we're plotting all the ordered pairs that satisfy the equation. There's an infinite number of ordered pairs that make that equation true. Same thing when we're graphing y equals 4 minus x. We're graphing all the ordered pairs, the infinite number of ordered pairs that make that equation true. So let's go ahead and do that. Let's graph each of those. I'm going to actually use different colors just so it's easier to see which is which and how to refer to them. So I'm going to use blue to represent y equals 2x plus 1. And so again, remember that that means that our slope is 2 and our y-intercept is 1. So that means we're going to start at the ordered pair 0, 1. That's our y-intercept. And we're going to go up by 2, right by 1, up by 2, right by 1. And we can do that a few times, and I'd advise doing it a few times. We can also go down 2, left by 1, down 2, left 1. And do that a few times until you get all the way to the end of the graph, really. The more ordered pairs, the better. And then we're going to connect the dots. And there's our line. So that's the one line. There's an infinite number of ordered pairs there. All of them are solutions to y equals 2x plus 1. Then we want to do y equals 4 minus x. Now this is written in the kind of reverse order, so don't get fooled by that. Realize that your slope is the coefficient of your x, the coefficient being -1. The y-intercept is the constant, so in this case it's 4. So for the red line, we have a y-intercept of 4, so that's where we start. And the slope of -1 says to go down 1, right 1, down 1, right 1, down 1, right 1. Now for this second line, we probably don't need as many ordered pairs, and I'll get into why in just a moment. So we go ahead and graph those. And again, there's an infinite number of ordered pairs there because besides the ones I put dots on, all the stuff in between, anywhere where there's red ink, that's a solution to y equals 4 minus x. So now we're going to take a step back for a second and look at big picture what's going on. Our goal here was to try to find the ordered pair or ordered pairs that satisfy both equations at the same time. The blue stuff is what satisfied the blue equation. The red stuff is what satisfied the red equation. So what we're looking for is an ordered pair that has both blue and red on it. That ordered pair would be the intersection. So that would be the ordered pair 1, 3. That's what the solution to the system actually is. It's the ordered pair 1, 3. The fact that we have a graph in front of us, that was basically our work. We were trying to figure out where that solution was going to be. We drew graphs to figure out where that intersection was. That intersection is the solution. So the solution is 1, 3. We could check this solution by plugging it into both equations and making sure it's true in both equations. So if I put the 3 in for y and the 1 in for x, I should end up with a true statement. 3 equals 3. And same thing for the second equation. If I put the 3 in for the y and 1 in for the x, I should end up with a true statement. And sure enough, it's true for both, so I know that 1, 3 is in fact the true solution to this system of linear equations.